So with that, let's go into scheduling. So as Chungyan mentioned, we're going to talk about a little bit about workload assumption. Now, these are simplified assumptions so that we could actually learn scheduling a little bit easier. But as you probably guessed, these assumptions are not realistic. Okay, the first assumption is each job runs for the same amount of time, right? They never do. All jobs arrive at the same time. Third, once they started, each job runs to completion, right? You can't preemptively, suspend or stop, right? So that's the initial assumption. Fourth thing, the process would only use CPU. In other words, they're not going to do any I/O. And the fifth is the runtime of each job is known in advance. So when we get the job, we know how long it's going to take, right? So these are the assumptions we're going to go with. Now, workload, same word as processes and jobs. So when we want to evaluate something, we always need a metric, right? What are we being evaluated on, for instance? So one of the metric for scheduling will be a turnaround time. So that's basically the time it takes since the arrival till completion, right? So I arrived, the job has arrived, and when it is over, completely over. So that's the turnaround time. It's like if you go to a restaurant, I arrived, and until I finish the meal, right? That's a turnaround time. Now, another metric is fairness, and there are different ways to actually quantify this. Like some of you might have heard about Jane Fairness Index. There are many variants of it. Typically, like is everyone or is every task being processed? Now, in most systems, fairness and performance usually they don't go well together. So there will always be trade-off, right? So that's something we'll also talk about a little bit later. So the first scheduling was something we're very familiar with, right? First in, first out, or first come, first serve. So the main strengths of this is easy to understand, so easy to implement, right? So an example here, job A arrived. Now they all arrived at the same time, like in our workload assumption, but A arrived just before B, which arrived just before C, right? And let's say each job runs for 10 seconds. Now, since A arrived first, that's 0, and takes 10 seconds. So you serve A till its completion, 10 seconds. Then you move on to B, fully for 10 seconds. Then C, first come, first serve, for 10 seconds. So if you do the turnaround time of this, right, we have 3 jobs. The A took 10 seconds from 0 to 10. B arrived at 0, took 20, right? Likewise, C arrived at 0, took 30. So you divide by 3. So average turnaround time, 20 seconds, right? Straightforward. Now, how do I remove this? Because I don't want to do audio. Anyways, never mind. Now we had 5 assumptions. Let's try to relax one of them, which first one was each job now no longer runs same amount of time. So different jobs might take different time to complete, which is more realistic. And let's see a situation where FIFO actually hurts in such case, which we call the convoy effect. So here, same thing, A, B, C arrive around the same time, but A first, B later, and then C. Now, difference now is A takes 100 seconds, while B and C each take 10. Remember, we're doing first come, first serve. So A gets served first. A takes 100 seconds, 0 till 100. Then B gets served for 10 sec. C gets served for 10 sec. So if you do the average turnaround time, now B and C also got penalized, right, because of A. So our average turnaround time is now 110 sec, which clearly no good, right? So we don't want to use first come, first serve in this kind of situation. Thus, we have SJF, shortest job first. So run the shortest job first, then the next shortest, and so forth. So this is, again, non-preemptive, meaning once you start, you get served until you complete, right? So in other words, let's say if you use a restaurant, let's say you're a restaurant owner, right? You don't take reservations. Perhaps the way for you to maximize your profit is whoever eats fast and get out, right? Versus like you order like the cheapest one and hangs out there for 3 hours while doing your computer, right? You don't want those kind of customers. So you want shortest job first. So example using the previous slide, right? Now in this case, when you start, I know A takes 100, I know B takes 10 and C takes 10. So I will schedule B and C first, right? So let's say we do B 10 sec, C 10 sec, and then takes 100 seconds to serve A. So just a little bit of tweak here results in a drastic reduction in the turnaround time, because now is 10 sec plus 20 sec plus 120 divided by 3, which becomes 50 sec, right? So shortest job first, another scheduling algorithm that probably helps you with the turnaround time. Now let's relax another assumption, this time assumption number 2, which said all jobs arrive at the same time. Now that assumption is gone, so they can arrive at any time. Okay, so now our setting here is A arrives at 0, and that runs for 100 sec. Now B and C, they arrive around the same time, but later than A. So they arrive around T equals 10. Now each need to run for only 10 sec, right? So if you remember in the shortest job first, there was a bullet point that said no preemption. So once you start serving, like in a restaurant, they don't kick you out in the middle of your meal, right? So no preemption. But now they're late arrivals. So you start serving A, you know it's going to take a while, but that guy was the only person at the restaurant at the time, so you start serving A, right? Then B and C arrive, and oops, B and C only take 10 seconds, but I have this rule, no preemption. So basically here, if you do the turnaround time, the only difference between the previous slide is that B and C arrive at 10. So there's minus 10 each here. The average turnaround time becomes 103.13 seconds. So SJF was good until we have some late arrivals that are small, short tasks. So the variant now is shortest time to completion first. So for this, we now relax assumption number 3. So jobs need not run to completion, meaning it could be preempted. Now, restaurants probably doesn't make sense. You still don't want to kick people out during the meal, but in the operating systems, we can, because we have timer interrupts, right? Remember, we have timer interrupts. I can reevaluate, and I can switch context. So STCF is now also known as, because it's preemptive shortest job first, PSJF. Remember, these are not MBTI things. Yes. So let's say a new job enters the system in the middle of something. Then what you should do at the timer interrupt is, what's the basically with all the remaining tasks, including the new one that just arrived, which one has the least time left? Then you schedule that one. So example here, same thing as the last time, right? A arrives at 0 while B and C arrives at 10. A runs for 100 sec, while B and C run for 10 sec. So here, A got served because it was the only task. At time 10, B and C arrive. So you reevaluate, right? A now has 90 seconds left, while both B and C only has 10 seconds left. So you're gonna schedule B or C, right? So let's say you serve B, it only took 10 seconds. After that, the remaining task is A and C. A still has 90 seconds left, while C has 10 seconds left. So following the algorithm, you schedule C. And at 30 sec, A is the only job. You schedule it. 90 seconds later, it's all done. So for the average turnaround time, right, for A, it started at 0 to 120, while for B and C, it's very short, so you get 50. So with preemption, we can achieve higher performance. So we have used turnaround time, but there's a second metric we want to go through today, which is the response time. So response time, so completion time is not one of the factors here. This is like when I start getting served. So this is a time from when the job arrives, the first time it is scheduled, right? So the response is when I arrive, then when do I start getting served? Not until completion, but when do I start getting served? Now, STCF and related disciplines, they're not usually good when it comes to response time. So how can we build a scheduler that is sensitive to response time? And that's where round robin comes in, right? So round robin is really time slicing, right? Basically, you run a job for a time slice, right? So you divide the time into little slices and you take turn, and each take slice, right? Oh, and by the way, time slice is sometimes called a scheduling quantum, but it's just FYI. Basically, you just keep doing it until your job queue is completely flushed. And obviously, the length of the time slice must be a multiple of the timer interrupt period. So round robin, since it serves everybody, it's fair, but it would definitely perform poorly on metrics such as turnaround time. So our scheduling example. So we have A and B and C. They arrive at the same time, and they each wish to run for 5 seconds. So if you do shortest job first, and they're all 5 seconds, so you go ABC, so 0 to 5, 5 to 10, 10 to 15, so the average response time will be 5 sec. While if you do round robin, but let's say we have a time slice of 1 second, then you take turn for each second, right? ABC, 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 you just keep going. So the average response time here is only 1 sec. Right, so you see the difference between shortest job versus round robin when it comes to trying to minimize the response time. Now, obviously, deciding on how long each slice is has a huge impact, right? And again, you have to consider the trade-offs, because if your time slice is short, that means you're going to have a really good response time, obviously. But then you have to context switch very, very often, which adds to overhead, right? On the other hand, if the time slice is long, then you don't have to switch often. But then again, response time would be very long, which is not good either. So again, many of the engineering problem is considering the trade-offs. Now, so far, we only thought about CPU, right? Each task only used CPU. But now let's relax assumption 4. And now we can say all programs can perform I/O. So example here, now we only have A and B, 2 jobs. And they both need 50 milliseconds of CPU time. Now A, what it does, it runs for 10 millisecond. then issues an IO request, which also take 10 milliseconds. So 10 millisec CPU, 10 millisec IO, 10 millisec CPU, 10 IO until you do the 5 CPU, 10 millisecond each. On the other hand, B, let's say, only uses CPU for 50 milliseconds, so there's no IO. So let's say a scheduler runs A first and then B after. Now, if you just serve A, right, CPU disk, and then B, versus when A is doing IO, then your CPU is idle. So you should schedule B here, right? So this is obviously much prettier than what you would do above, right? So you want to maximize the CPU utilization. So when a job initiates an IO request, that job is blocked until the IO is completed. And then scheduler should schedule another job on the CPU. And when the IO is completed, an interrupt will be raised, and that job that was on the block list now needs to get back to the ready state. And then the scheduler will decide whether you want to go back to this process or whatever process based on your scheduling algorithm. Right, the fifth assumption that we're going to relax is the scheduler does not know the length of each job. And then the transition is to go to the MLFQ because if you guys remember, the beauty of it is it does not require prior knowledge. Okay, so now we're back on the schedule. Any question?